Yeah, hello guys. I welcome you to this video. Trying to solve tutorial sheet number 5. So I actually solved it, and I'm just going to help explain a bit on how you can actually solve on your own. Okay, so I've reserved one question for your assignment. You are going to attempt, and then you scan, make PDFs, and then I'll attach an email as I send this video to you. Okay, so we have question 1 there, tutorial sheet 5. It's based on momentum here. Okay, so I'm going to assume that you guys are up to date with your lessons. Yeah, so I'm just going to run you through this tutorial sheet. Okay, so question 1 here, basically what it's saying is that there is one car, which is going to be our first car, which is at rest, and then there's another vehicle coming from behind. Okay, so the second vehicle comes to hit the first vehicle, which is at rest, and then they skid together for about 6 meters in the original direction of motion. Okay, so as they are skidding, guys, their brakes are applied. Okay, and because their brakes are applied, it means there is some friction there. So we're going to have some work done by friction. Yeah, so we're being told that the stopping force is going to be 0.7 times the combined weight of the cars. Okay, so yeah, that 0.7 is basically mu. So here, as you can see, okay, so as you can see here, we have this equation to say as the vehicles begin to skid, there's that change in kinetic energy. Okay, because they are moving and they are going to move with the speed v. Okay, but because their masses are combined together, we are going to have 2m instead of just m. Okay, so here to start with, we have change in kinetic energy being equal to the work done by friction. Okay, where the work done by friction is simply the normal force times the distance covered. Okay, like that. So we know what the normal force is. It's simply the coefficient of friction multiplied by the weight of the object. Okay, so this equation, the change in kinetic energy, therefore we have half 2m v2 squared. Okay, notice that we're using v2 here because it is the final velocity for both. Okay, for both vehicles, because they're skidding together and they're covering the same distance, so the final velocity will be for both vehicles. Okay, so change in kinetic energy, we have half 2m v2 squared being equal to 2 mu mg times the distance. Okay, so again, this 2 here on the right hand side is simply there to show us that we are considering the mass for both vehicles. Okay, so it is 2m times the mu, which is the coefficient of friction, and the weight of the vehicle multiplied by the distance they are both covering. Okay, so if you work it out, we are going to see that the mass will actually cancel out from both sides. As you can see there, the mass is going to cancel out, and the equation is going to remain v2 squared equals 2 mu g times the distance. Okay, so once the masses have cancelled out, and then we remain with this equation here, and after all, we have the data in the question. all we need to find is the final velocity for both vehicles. Okay, so now we simply substitute the data into the equation here. We know that v2 squared is going to be 2 times 0.7 times 9.6 times 6. Okay, so it's going to give us that. All right, so after you work it out on your calculator, you're going to find 82.32, and then if I get the square root of that, and that is going to give you the final velocity for the vehicles as they are skidding. Okay, so once you have done that, you are going to get your final velocity as 9.07 meters per second. Okay, so now we know the final speed of both vehicles. Okay, so what is remaining now is we now have to find the initial velocity of the second ball, the ball that was coming to hit, the second vehicle. Okay, the vehicle that was coming to hit the first vehicle, which was at rest. So now we have to find the initial speed of the second vehicle. Okay, so now to do that, we are going to consider the conservation of linear momentum. Okay, this is where we begin actually. The conservation of linear momentum therefore gives us this, okay, in green here. So we have that m1 u1 plus m2 u2 equals m1 v1 plus m2 v2. So this simply means that the momentum before the collision must equal the momentum after the collision. Okay, so now we know that the first vehicle was at rest. Okay, meaning that the initial velocity of the first vehicle is 0. All right, yes. Okay, so because the first vehicle was at rest, we have that u1 is equal to 0. Okay, and because u1 is equal to 0, that one will definitely be out of the equation. And then the mass of the first vehicle is equal to the mass of the second vehicle, which can simply be considered as m. Okay, so if we rearrange the equation, we are going to have 0 plus m, because it doesn't matter whether it's m2 or m1, it's just m. Okay, so now it becomes m u2 equals okay, equals m v1 plus m v2. Okay, again we know that the final speed of the first vehicle and the second vehicle are the same. Okay, v1 therefore is equal to v2, which is what we just found. Okay, so now our equation for the momentum remains u2 equals v2 plus v2. I hope you're following. Okay, here we're having v2 plus v2. Why? Because the v1 that we had is equal to v2. Okay, so meaning either v1 can be v2 as well, or v2 can be v1 as well. All right, so now we are saying u2 is equal to 2v2. Okay, so then we mean the initial speed of the second ball is going to be twice the final speed of both vehicles. Okay, we're going to get this. Okay, and finally we solve and we're going to get 18.14 meters per second as the initial speed of the second car. Yes, second vehicle. Otherwise, that's just that. You have to consider the change in the energy there. We know that these objects are moving, so you take into account also the energy changes, and then you also consider the momentum of the system. Okay, so that was on question 1. Okay, so now coming to question 2. Question 2, here we have a bullet. Okay, so this bullet is traveling at an initial speed of 500 meters per second. It has a mass of 10 grams and it strikes a 2 kg block. Okay, this block, which is suspended by a string of length 5 meters. Okay, so what's happening here is that this bullet, okay, this bullet is going to strike this block and then it will pass through it like that. Okay, so it's going to emerge on the other side, and as the block is being hit by the bullet, of course it's going to move. Okay, it's going to move, but because it's attached to a string, its motion is such that it's going to go high like that. It's going to gain a height. Okay, if there was no string attached, this bullet would have probably gone straight in the same direction as the bullet. Okay, but because there's a string there, it's going to gain some potential energy. Okay, it will rise, as the question says. It's going to rise a vertical distance, in this case of 10 centimeters. Okay, so meaning as it moves, there's a change in kinetic energy there, which leads to the gain in potential energy. Okay, so again, we have to consider the energy change here as well as the momentum of the system. Okay, so we have two objects. We have the bullet as well as the block. Okay, so for the bullet, the momentum of this bullet, we are given, we have m1. We are going to consider the bullet as m1. Okay, so m1 is moving with an initial velocity of u1. Okay, m1 with an initial velocity of u1, and it's going to have some final speed after emerging out of the block. Okay, so m1 u1 equals m1 v1. Okay, so this is the momentum of the bullet. Okay, so what about the block then? The block will be considered as m2 here. Okay, so if the block is considered as m2, we are going to have m2 u2 equals m2 v2. It's going to have the initial momentum and also the final momentum. Okay, so now for the block, notice that initially the block is at rest. Okay, meaning that the initial speed of this block is 0. Okay, so if u2 is 0, then it means the initial momentum of this block is 0, and therefore we only have the final momentum. Therefore, for the block, the equation for the momentum is going to be 0, which is the initial momentum, equals m2 v2 as the final momentum. Okay, so then because the system, we are dealing with both the bullet and the block, we have to write, or rather combine, the momentum and work it out in totals. Okay, so we are going to have the total momentum before the incident being equal to the total momentum after the incident. Okay, so before the incident, we have the momentum of the bullet, which is m1 u1, plus the momentum of the block, which is m2 u2, equals the final momentum of the bullet plus the final momentum of the block. But we know that the initial momentum of the block is 0. Okay, therefore we are going to remain with the initial momentum of the bullet equals final momentum of the bullet plus final momentum of the block. Okay, yeah, well, I hope you're following, guys. You are going to solve this somehow. I know somewhere you're going to go through them again. So yeah, okay, so that's what we're getting here. Okay, so after having gotten that, we can substitute with the values that were given in the question. We know that the mass for the bullet, which is M1, is given as 10 grams, which is 0.01 kgs. Okay, and the initial speed for this bullet were given as 500 meters per second. Okay, so it's going to be 0.01 as the mass multiplied by the initial speed, which is 500, equals the mass of the bullet times the final velocity of the bullet, which is unknown at this stage, plus the mass of the block, 2 kgs, multiplied by the final velocity of the block, which is also unknown at this stage. Okay, so then what we want to find here in this question, okay, what we want to find here in this question is the final speed of the bullet as it emerges from the block. Okay, so when we look at this equation, it means though we want to find V1 only, we also need to know what V2 is. Otherwise, we're going to remain with two unknowns. Okay, so let's find what V2 is, and then after finding what V2 is, we can easily find V1. Okay, so with this equation, after multiplying that 0.01 and the 500, it's going to end up like this. Okay, it's going to end up like this. Right, so we have 5 equals 0.01 V1 plus 2 V2. Okay, so now we go to the energy change. Remember what we said about the energy. This system consists of objects that are moving, and if an object is moving, then it possesses kinetic energy. Okay, so in this case we have a block which is hit, and then it gains kinetic energy, which is later lost and converted to potential energy. Okay, as it rises a height of h 10 centimeters. Okay, so now we're going to say that the change in kinetic energy of this block is equal to the gain in its potential energy. Okay, so now we are going to have this, the change in kinetic energy of this block is going to be the gain in its potential energy. Okay, we get that. So now half m2, because the block is m2 in this case, and its final speed is also v2, therefore, well, the initial is 0, so there's no need of showing that final minus initial, because the initial is automatically 0. Therefore we simply go straight, and we have that half m2 v2 squared equals m2 gh. Okay, so that's what we're having there. All right, so when you look at this equation, you can easily tell that we can find v2 from this. Okay, we can find v2 from this. All right, so the second mass we're given as 2 kilograms, and if we substitute into this equation on top there, we're going to remain with v2 squared equals 2 times g times h. Okay, 2 times g times h. Okay, so then we have that v2 squared equals 1.96, and if we get the square root of that, we're going to find v2 as 1.4 meters per second. Okay, so this is the final velocity of the block. Okay, so now we go back to our equation 1 here. Okay, we substitute the value of v2 and then we find v1. So we know that v2 now is 1.4 meters per second, and when we substitute, we're going to have 5 equals 0.01 v1 plus 2 times 1.4. all right, so now if we work that out to solve for v1, this is what we're going to have here. Okay, giving us our v1 as 220 meters per second. Okay, so and then we're done with question 1. We were simply looking for the final velocity of the bullet after it passes through the block. Okay, so question 3 now. So question 3 here, we have 2 balls, billiard balls, one at rest and the other one moving with a speed of 6 meters per second. Okay, so this ball that is moving with this speed is going to hit another ball which is at rest, and after that, after the elastic collision, the balls are going to move in different directions. Okay, so we can make the xy plane as reference in this case, where our original motion for the first ball will be considered as we are just going to take it like it's going towards the positive x direction. Okay, so it's moving in that direction. It's going to hit the second ball, this guy here. After it hits the second ball, it moves from its direction at an angle of 25 degrees. Okay, so it's going to end up somewhere there, right? So as it moves like that, it's going to have some final velocity with it, and the other ball which was at rest after being hit also does not move in the original direction of the x, but also makes an angle alpha with respect to the original direction. Okay, so when you see this, we have to know that, okay, we have a system that is changing direction with respect to the initial direction. So in this case, we have to consider the components of the speed. If we are finding v1, we have to consider v1 in terms of x as well as in terms of y. Okay, the same goes for v2 here. We have to find v2 in terms of x as well as in terms of y. Okay, so that is what we're going to do here. So we're going to find the final speeds of these balls, both of them, and then also find the direction for the second ball, the ball that was at rest. Okay, so first off, let us see let's see the conservation of momentum. What does it give us? Okay, what does the conservation of momentum give us? So for this system, we have 2 balls. So notice that for the second ball, the momentum is grayed out, meaning that it's going to be out of the equation because its initial velocity here is 0. Okay, the second ball is at rest and the first ball is the one which is moving, okay, with that given speed. Okay, so then we have that m1 u1 m1 u1 equals m1 v1 plus m2 v2. Okay, because u2 is 0, m2 u2 is going to be out of that equation. Okay, so yes, this is what we're having here. Because u2 is 0, we're going to have m u1 plus 0 being equal to m v1 plus m v2. Okay, notice that we're using m here because we're saying that m1 is equal to m2, which is simply m. Okay, so we are going to factor out the mass on the right hand side, and then it can simply cancel out. As you can see, it's grayed out here. We're going to remain with u1 equals v1 plus v2. Okay, therefore we can call this our equation star. All right, so this is the equation of the system. We have u1 equals v1 plus v2. Okay, so we know what u1 is, but we don't know what v1 and v2 are. Okay, so now we consider the components. The x component of equation star here is going to give us u1 in x. Okay, u1 in x equals v1 in x plus v2 in x. So notice that it's the same equation. Okay, same equation, but now we want to deal with it in terms of its components. Okay, so the x components are going to give us this, and then we have those angles there on the diagram. We have those angles on the diagram. Okay, so if we're considering v1 here, u1x, of course it's moving in the x originally, so it's simply 6 meters per second, and v1x therefore is going to be v1 cos 25. Okay, and v2 is going to be, v2x is going to be v2 cos alpha. Okay, well, I'm sure you've done these vectors. You can go back to the vectors, and then yeah, so here what we have is u1x is 6 because the ball was initially moving in the x direction, and then v1x, this is u1x, v1x is going to be v1 cos 25 because this is the angle it's making with the x-axis, or rather the original direction. Okay, and v2x is going to be v2 cos alpha. All right, so this is what we are having, and then we can simply rewrite it in terms of v2 cos alpha being equal to 6 minus v1 cos 25. Okay, so we can call this our equation 1. And then we go to the y component. So we have u1y equals v1y plus v2y. All right, so notice that originally the ball is just moving in the x, therefore the initial y speed is 0. Okay, so we have that 0 equals v1 sine 25 minus, okay, so minus because it's heading towards the negative y-axis, so it is minus v2 sine alpha. Okay, so you can rewrite this in this form, and then it becomes our equation 2. Okay, so now we are going to square equation 1 and also square equation 2 and then add them. Okay, so when we square equation 1, we're coming up with this. Okay, we square equation 2, we're coming up with this. Okay, so after squaring them, we're going to add them now. Let us add them, and when we add them, we're going to have this guy over here. So you guys should actually do this. Okay, make sure you're solving somewhere on a piece of paper to make sure you are actually getting what's happening here. So we're going to have this guy like that. Okay, so we have squared equation 1. Okay, so notice these identities. You have done trigonometry and you're simply going to be getting ones out of these. Okay, cos squared alpha plus sine squared alpha is simply 1. Cos squared 25 plus sine squared 25, it is going to give you 1. Okay, so when we add them, yeah, right there, I said it. Note that cos squared theta plus sine squared theta is 1. So you simply replace wherever you see this identity with a 1, and then we're going to remain with this guy right here. Okay, so now we have squared both equations and then we have added them. All right, so after adding them, this is our equation 3 now. Okay, we've added 1 and 2 and we've come up with equation 3 in this form right here. Okay, so after reaching here, we pause and then let's see how the energy is changing for this system. Okay, so for the energy change, we have that the kinetic energy before should be equal to the kinetic energy after. Okay, kinetic energy before should be equal to the kinetic energy after. So for the second ball, the kinetic energy before is obviously 0 because it was at rest. So we have the kinetic energy for the ball which was moving with an initial speed. Therefore we have half m1 u1 squared equals half m1 v1 squared plus half m2 v2 squared. Okay, so we have kinetic energy before equal to kinetic energy after. All right, so we know that the masses are equal. And we have halves on both sides. As you can see, the half m is going to cancel out and you remain with u1 squared equals v1 squared plus v2 squared. Okay, therefore we can have this equation as a star. All right, so now that we have star here and we know that u1 is 6 meters per second. Okay, let us not forget this, we have been given. If we substitute this u1 into equation star right here, we are going to have that 6 equals v1 squared plus v2 squared. Okay, so now this is our modified version of equation star. Now we are going to substitute this equation star into equation 3 right here. Okay, we're going to substitute. So where there's 36 here, notice there's 36. Okay, so this 36 here, we are told that it is equal to v1 squared plus v2 squared. Therefore we are going to put where there's 36 in equation 3 and it's going to be v1 squared. Okay, so where I have put this v1 squared plus v2 squared is where the 36 it was supposed to be in equation 3. Okay, therefore we're going to have that minus 12 v1 cos 25 plus v1 squared equal to v2 squared. Okay, So then after that, we notice that the V2 on the left hand side and the V2 on the right hand side are going to subtract, and they will be out of the equation, and the V1 squared is going to add with the other V1 squared, like that. And then we're going to have 2V1 squared minus 12V1 cos 25 equals 0. Okay, well, this is just some mathematics, guys. Shouldn't be confusing at all. Okay, so from this, if we actually work it out, we're going to discover that V1 is equal to 6 cos 25. Okay, just keep working this out. You can take the you can remain with 2V1 squared equals 12V1 cos 25, and then simply solve for V1. Okay, that's how you reach at this stage. Okay, so after doing all that, you're going to find your V1 as 5.44 meters per second. Okay, so now that we have found our V1, we can easily find V2. Okay, using which equation? We can use equation star, this one right here, the orange one. Okay, 36 equals V1 squared plus V2 squared. So now that we have our V1, you can simply substitute the value of V1 into this equation, and then we also solve for V2. Okay, so let's do that. We now find V2 using equation star. Then we have that 36 equals V1 squared. Okay, this is V1 squared plus V2 squared. So now it is very easy to solve for V2. We have that V2 is going to be the square root of 36 minus V1 squared, and then we have our V2 as 2.53 meters per second. Okay, very easy. All right, very easy. So we have found V2 here. So next we are going to find the direction of the second ball. The direction of the second ball, we simply find the angle with which it makes with the original direction. Okay, so we are saying here to find alpha, we are going to consider equation 2 squared. Okay, we remember equation 2. Kindly go back. You can always take the video back and check which one is equation 2. Okay, so equation 2 is given as V1 squared sine squared 25 equals V2 squared sine alpha squared. Okay, so since we are looking for alpha, we are going to say sine alpha squared equals V1 squared sine 25 squared divided by V2 squared here. All right, so we work that out, and then we're going to have that, and then it's going to end up like this. All right, you guys know what is happening here. All these are under the square root, so whatever is squared will simply be not squared anymore. Okay, it's going to cancel out with the square root sign. Right, so then we have that sine alpha equals 0.91, and we can find alpha as the sine inverse of this 0.9. Okay, and it's going to give us 65.4 degrees. Okay, so this is the angle that the second ball makes with respect to the x-axis, or rather the original direction. Okay, so make sure you're following through the steps. You can always take the video back. That's why it's a video. If you're not clear, take it back, listen again, follow through as you are solving on your piece of paper. This is just for reference, okay, to guide you. You have to do this. You have to do this. Okay. So now that we have found the final speeds for both billiard balls and the direction for the ball that was at rest, I'm sure when you go back through the video, you'll be able to pick up something. Okay, you can pick an idea here, you can totally get it and be able to solve the question whenever you meet something of this nature. Okay, so we are dealing with this. That's just my rough sketch. Of course, you can always picture it and try to sketch before you go direct into the calculations. It will help you. It's going to guide you. Okay, so we go to question 4. Question 4. Okay, so hopefully question 4 is the last, because I want you guys to attempt question 5, and yeah, just gauge yourself. I want to see how you're going to try and solve it. Right, so question 4, we have a vessel which is at rest. It's not moving, it's just at rest, and then it explodes. Okay, so when it explodes, there is like there are 3 particles that are ejected. Okay, how can I say it? It breaks into 3 pieces like that. Okay, so we're being told that 2 of these pieces have masses m1 and m2, where m1 is equal to or rather is twice m2, and they fly off at 90 degrees with each other with the same speed of 30 meters per second. Then the third piece, which is 3 times m2. Okay, so for this third piece, we're going to find the velocity as well as its direction after the explosion. Okay, so excuse me. So the first thing we need to consider here is okay, so the first thing we need to consider here is how it actually looks, or how you can actually picture it. Okay, so we have this vessel here at the center. It explodes, and we have m1 going in the x direction and m2 going in the y direction. So m3 is making that angle phi, which is shown there. Okay, it's making an angle phi with the negative y-axis. Okay, hope you can see it. So now we have to find v3 as well as its direction. Okay, so let us see the momentum of the system. How can we write the total momentum for the system? Okay, we know that initially at rest, none of these particles, the 3 particles, none of them is moving. So because none of them is moving, it means the initial momentum for all 3 particles is going to be 0. All right, so it's going to be 0, and we're only going to remain with the final momentum for all the particles. Okay, because each particle is going to move in a given direction and at a given speed. Now for these other 2, m1 and m2, we know that the speed is 30 meters per second. Okay, the speeds are equal. Okay, so now let us come here. It can also look like that. Okay, so m1 v1 along the x, m2 v2 along the y, and we have m3 v3 making an angle here, an angle, I'll call it alpha. Okay, So this guy, we know that actually to find this angle, we have to come like that. That's how we measure the angles, not so. Okay. So the momentum of this system, when you look at it, we have V1 in terms of components. We have to consider their directions. So V1x, are you able to see where V1 is? It's moving along the x. So we're saying that V1x is simply V, which is 30 meters per second. Okay, that is the magnitude of the velocity in the x. But in the y, this V1, or rather M1, is not going anywhere near the y direction. Okay, it's just moving along the x. So V1y is 0. And then we also have V2x being 0. Okay, V2x being 0. This ball here is not moving in the x, but it's just going in the y direction. Okay, so because it's going in the y direction, it has 0 x component. Therefore, the y speed of this second particle is the same as v, which is 30 meters per second as well. Right, so the other thing we consider here is that m1 is simply twice m2, and and m3 is 3 times m2. Okay, so from that we can write our momentum, rather the conservation of momentum. Momentum before should equal momentum after. So we know that momentum before is 0 for all the particles, and the momentum after is given by this. Okay, this is the momentum after, and this is what we are dealing with. Okay, therefore we have that 0. Since we know excuse me, since we know that m1 is twice m2 okay, so it's going to be 2 m2 times v1 plus m2 v2 plus m3 is simply 3 times m2. Okay, so it will be 3 m2 times v3. So this is our equation 1. Okay, that is the momentum of the system. And then we consider now the components. We know that v2, rather m2, is not moving in the x, but it's moving in the y. Okay, we have the x equation, rather component of equation 1. We have 2 m2 v1x plus m2 v2x plus 3 m2 v3x equals 0. Okay, so we know that v2x is 0. Therefore this equation is going to be 2, okay, m2 v1x plus 3 m2 v3x equals 0. Okay, so notice that we have m2 moving out of the equation here because it is equal on both particles. We have particle 3 and particle 2 here. No, particle 1 and particle 3. Okay, so when we cancel out the mass, we are going to remain and rearrange this. We are going to remain with 2 v1x plus 3 v3x equals 0. Okay, and when we remain with that, we can express v3 and actually find the value of v3. Okay, so when you rearrange that equation, you're going to remain with v3 equals minus 2v1x over 3. Okay, we know what v1x is simply v, which is 30 meters per second. So we substitute this 30 meters per second into the equation for v3x, and we're going to have v3x as minus 20 meters per second. So we have found the x component of this v3. Okay, so now that we have found that, let's see the y component. How can we find the y component of this? Okay, so we rewrite our first equation there again, but in terms of y, we have 2m2 v1y plus m2 v2y plus 3m2 v3y equals 0. Okay, but again, one thing we know is that v1, rather m1, is only going in the x, therefore v1y is 0. Okay, take note of that. So if we put 0 there, then it means that we only remain with m2. Okay, we only remain with m2 v2y plus 3m2 v3y equals 0. We take 1 on the other side of the equal sign, it remains negative, and we have negative, okay, the negative there, negative m2 v2y equals 3 m2 v3y. Okay, notice that the m2 and the m2 on both sides are going to cancel out, and we remain with v3y equals negative v2y over 3, giving a minus 30 here over 3, and we have our v3y as minus 10 meters per second. Okay, so we have found v3x as well as v3y. So now we can find the magnitude of v3, and we know how to do this from the time we've been doing vectors. So we know that v3 therefore is going to be the x component of v3 squared plus the y component of v3 squared, like that, under the square root. So we're simply finding the magnitude here. We keep on doing that, and we have v3 as 22.4 meters per second. Okay, so if I'm moving too fast, please just go back. You can pause the video, check through where you are behind, rewind. Okay, so now we have found the final speed of m3, the third particle. Okay, so now that we have found its final speed, we are remaining with the direction. Okay, let us now find the direction of this third particle. So to find the direction, we know how to do that. We're going to use the tangent. You have tan alpha equals v3y over v3x, where our v3y is minus 10, our v3x is minus 20. Okay, so the alpha equals tan inverse of 1 over 2. So this 1 over 2 is coming as a result of negative 10 over negative 20. Okay, so we have 1 over 2, and we are getting 26.6 degrees. Okay, so that is the distance we're getting. Okay, so with the knowledge that we have, we know that this angle is simply an addition. When we look at the diagram, even just the setup of that, we are adding 180 plus 26.6, giving us 206.6 degrees. Okay, so I'm sure by now you know how we are going to, why I'm adding this 180 here. Okay, you are going to use that method, mathematics, the reference, the what. Okay, that is okay. So Yes, so this is question 4. We have now found the direction of the third particle as well as its final speed. All right. Okay, so just make sure you go check through, go read, and yeah, for reference, you can always ask anyway. You can always ask. You can always ask. This is just a tutorial to guide you on how to solve actually on your own. So there shouldn't be much trouble. Okay, so I'm going to send also the file that I have used to record this video, so you can just read through. Okay. All right, so thank you. We are going to be dealing or rather doing this instead of using Google Meet or Zoom, because some people are having issues logging in. So I think this is better, because whenever you come online you find the video, just download and you watch offline. Okay. All right, next time guys.